Dorothy, run the diagnostic on the last batch of learners. Why is the retention rate sitting at 10%?
It's a hardware limitation, Norm. The human brain runs on 20 watts of power. It filters 99% of input to preheating. The remaining 1% is degrading before it reaches long-term storage.
I see. You don't have a discipline problem. You have a hardware problem. Today, we audit the source code. Let's get started.
All right, all right. Welcome back to class, learners. Hopefully you all are safe from the winter storm that just hit us in the southeast and in the south. Hopefully you have your power restored. You're able to get all of your necessities and your orders and affairs in order, excuse me. And hopefully you're staying warm too. So welcome back to class. This is the introductory course to natural intelligence, the blueprint for AI. I am your presenter and trainer, Ryan Norman, aka Norm. Now, remember, before we start talking about artificial intelligence, machine learning, large language models, or AI agents, we're going to take things back to first principles. And this is a step that most technical education currently on the market skips entirely. They do not go over how information moves through the human brain. Or in other words, they do not teach their learners how to learn. And that's an objective, a key objective of my course and my materials, is to make sure that I'm empowering all of you viewers, all of my students, with the skill of lifelong learning, because we don't entirely know what skills or which skills will be the cream of the crop in the next few years or decades, but we can be fully assured that it will involve us having to learn. So why not focus on that? Focus on making ourselves better learners, more engaged learners, more excited and interested learners, and have fun in that particular skill set. And from there, we can start to build and stack other skills on top of that. Now, today's lesson is the source code. This is lesson number 1. And in the source code, something you want to think about, or something we all think about, we are entirely obsessed with the artificial. That's artificial intelligence, artificial sweeteners. And we talk about all these token limits, context windows, fine tuning, inference, chips, all of these things. But we're trying to build a replica of a system that we haven't even bothered to audit yet. And that's our human OS, our human operating system, our brain, our intelligence. And I'm calling this the source code. And today we're going to audit that system. The central goal for this lesson is to map the Magnificent 7 axioms. We'll talk about what each one of those are. And we're going to map those 7 axioms to the flow of information in both human brains and computers. This will serve to establish that reference diagram for the entire course in all of the lectures to come after. We're going to analyze biological constraints, identifying the hardware limitations of the human brain, such as filtering out 99% of sensory input and forgetting 50% of information within an hour. Then finally, we'll perform an activity of a system audit using the Magnificent 7 axioms to conduct an autopsy as such on a failed learning experience that we've had in the past year. And we'll try to identify exactly which cognitive axioms were violated from those 7 axioms. Now that we know what the objectives are, let's get started. The core content is going to be the information processing model, right? Our input, our process, and our storage. Now, this is the information or data pipeline, and everything you've ever learned follows this path. Data enters in, coming in. That data then turns into input or some type of structured input or a network. And that input either gets processed, okay, or it ends up getting filtered out, okay? Ends up going to the garbage can, right? And our ability to process this information is what allows us to eventually turn it into storage or stored information, long term memory, either long term or working memory, for us to be able to recall in the future. But something's important to note is that storage is not automatic and it's earned by this processing of the information. If you don't process the information, it will get filtered out. Okay? Something for us to remember here, keep in mind as we are learning about the material here. Another side note here as well, each of these lessons or axioms that I'll be covering, which will be the Magnificent Seven here that you see on your screen, these are just going to be previews for today of these seven. We'll go in depth in each one of these in future lectures, and they'll each have their own lab. But today is just going to be a preview. Just keep that in mind. We're just kind of going at a high level of each one of these axioms just to introduce them to you. The first axiom is the gatekeeper. Right? If your attention doesn't grab it, it doesn't exist in your brain. Now, here's a visual that I think will help you understand this. We have this stimuli over here. Okay. And the stimuli can be everything from the videos we watch, right? Videos can be our social feeds, right? Maybe our conversations that we're having with individuals, right? We're having conversations. And anything as far as data, right? We essentially call this data, is going into this gateway, right? Now, the gateway's job is to essentially filter. Okay? Its role is to filter. And we have something in our human brains called the RAS, or the reticular activating system. Okay? Now, this reticular activating system, or RAS, it serves as a selective filter. Okay? And it's designed to conserve as much energy as possible. The way our brains have evolved over millions of years is that we need as much information, or excuse me, we need as much energy as possible in order to be able to survive. Now, this gatekeeper helps us select and filter the things that are important or salient. Okay? And if it's not important, it gets ignored, right? Essentially gets filtered out. We don't hold on to it, it gets deleted. Now, the AI bridge in our large language models, our LLMs, they have a process similar to this. And this is going to be where we have essentially a prompt or prompt engineering. And through prompting or prompt engineering, we also filter, or the large language model filters. We filter the information that can potentially be generated from that large language model. And so it may not be exactly the same as the gatekeeper acting in our human brains, but it does serve as a very similar filtration system in the artificial world. The next up is the bottleneck axiom. You can only hold so much before you start dropping the ball. You ever try to take in a massive amount of information or try to cram a whole bunch of data again, right? Data flowing in. You ever feel overwhelmed taking a course, new training, new information, trying to listen to a lecture, trying to listen to maybe one of your friends tell you a story? Well, we have these bottlenecks, or a bottleneck that limits us to about 4 chunks of information, plus or minus, give or take. And this is called the cognitive load theory. Right? It's our ability to retain or hold information in our working memory, but it can only be a certain amount of information that eventually flows through to our brain. Everything else essentially becomes trash. It gets filtered out again. Remember, our brains are supremely efficient. Now, LLMs have something similar as well. Our AI models have what's known as the context window. Okay? And their context windows are essentially their bottlenecks or one of their many bottlenecks when it comes to storing the amount of tokens that that context window can maintain. Now, if you don't know anything about token limits or context windows as it pertains to AI, don't worry, we'll get there. But as of right now, just understand that our brains are limited with how much information we can hold at a time, or at least within one setting or ingestion. Next up, we have parallel processing. And this can be broken down into using, for example, our eyes and our ears together to increase our bandwidth of information or data ingestion. There are two separate roads that essentially allow for double traffic or increased capacity. Now, the biological basis is grounded in what we call dual coding, also dual channel theory, right? In this duality, as you can see, our ability to look at visual information as well as verbal or textual information through separate channels, but merging them together, this synergy, right, creates this integrated understanding, right? And it's double the capacity, but there is a potential for overwhelm. If you try to, for example, view information that is not related to the verbal information. Let's look at the slide here now. I'm talking about parallel processing. Well, if you're looking at the slide, this infographic on my screen here for parallel processing, but if I started talking about the previous axiom, the bottleneck, then you are hearing verbal cues and verbal data from one channel with entirely different information that you're seeing in another channel or your visual or spatial channel. That can cause a conflict and essentially cause you to crash. Now, we call this multimodal or multimodality in large language models. And we know this by the way we use our ChatGPTs, our Geminis, our Claudes. They're great at image generation. They can generate audio for us. And of course, they can also generate text for us. And this is what we consider to be a multimodal processing engine or AI system. And it's very similar to our parallel processing that we have within our human brain. Next up on the list of axioms is the knowledge graph or the principle of schemas. Now, the brain doesn't store files in an isolated manner like a file system or file directory system that you might see on your computer. In fact, what it actually does is it builds these webs. Okay? It actually builds webs, not isolated files. So this is grounded in what we call the constructivism in schema theory. If you don't know what a schema is essentially just a blueprint or a scaffolding that holds information or data. And for those of you that have a little bit of experience in tech, you may have heard these in relationship to databases. But we also have sort of a schema available for us in our neural networks, which are both human and also artificial, because we've replicated that. So these schemas are going to hold information for us or clusters of meaning. Now, something important to note is that new information, it can really only be hooked into this scaffolding to existing schema or data. Now, think about this when we start to use analogies or similar relationships or relatable information. What you're doing is you're hooking new data to old data. And when you do that, right, you'll be able to, again, expand the web by hooking in. Now, if you don't hook in, you'll get what's called essentially this orphan node. And when you have orphan nodes that don't get essentially this hook, right, they don't get hooked or attached to existing information, what ends up happening is that information gets forgotten or purged out. Now, just as humans, large language models also rely on this semantic proximity or relationship building, the semantic relationship. And we'll talk a little bit more about vectors and embeddings when we get to our section of the course with AI models. But just know as of right now, vectors or embeddings are essentially the machine code or machine learning of text to numbers, quantifiable text. Moving on to our next axiom, we have coming to the stage the compression algorithm. Now, the compression algorithm is the principle of active processing because intelligence is not a storage bin. Right? We just saw in our previous example how our brains act as networks, not necessarily file cabinets. Well, with this active processing, the compression algorithm or the compression engine that we have inside of our brains, what it essentially does, it stores information not just for usage later on, but it actually encodes our memory in our brain by actively manipulating, summarizing, and reconstructing all of this raw data that you have. Okay, so it means nothing to be passive in the consumption of your data. In fact, what you want to do if you want to be actively processing or generating output from that consumption. So, for an example, if you're watching a YouTube channel or YouTube video like mine, you don't just want to watch it, you also want to generate something from this. Maybe you go tell a friend about it. Maybe you build your own slides or make your own connections or notes about the information. Right? But you're somehow trying to generate output. And that's where the learning actually happens. That's where you get the learned and encoded memory after you've generated that output. Now, we see AI models do this with the weights and biases, the parameters that eventually become the learning of the machine model. And also the generative model does this. Okay? So every time we generate information from an AI or every time an AI generates information for us, it is predicting and comparing, essentially trying to find the next tokens. And that is what we call essentially inference when it starts to do that. And if it doesn't reach that point, that model is pretty useless. All right, moving on to the query function. Now, the query function or the principle of retrieval is the act of querying the brain or searching the brain. And this is what signals the biological system that this information is worth keeping. Okay? Again, passive review is not what we want. We don't want passive review or passive consumption. This leads to weak or fading pathways. In other words, information just eventually gets filtered out and thrown away or forgotten. But true learning comes from this muscle principle of retrieving, actively retrieving information or knowledge, strengthening these neural pathways in our brains, okay, in that network of nodes, continuously and repetitively updating the weights and biases, so to speak. And that's exactly what's happening in the artificial. Let's take a dormant model again, very useless unless it's doing the active inference, right? If it's not doing any inference, it's useless. We don't need it. So we actually have to take in our query or our prompt. Right? From that prompt, we do some active processing or active inference, and that's going to give us some generation, right? Some generated output, the next token. All right. And on to the final axiom, which is the save protocol. Now, this is the principle of consolidation. And this is when the brain defaults to deletion. Right? This is grounded in what known as also called the synaptic, okay? The synaptic consolidation. Right? Now, what does that mean? If you don't reinforce as time passes, if you do not do this, okay, let's say you don't do that, your brain will automatically delete information without any reinforcement. If you sit down and read a book and you never recall any messages or passages in that book, you don't share any of the data or information that you've learned, if you don't use that information, your system will delete it, likely by the end of the day. The only way to save or consolidate that information is through what's called spaced repetition, getting in the reps. Okay? And this is structured exposure of that information in different scenarios. Right? So that eventually leads to what's known as the permanent long-term storage that we need, right? Or long-term memory. But that does not happen if we don't have a number of repetitions for the information that we are processing. So as I'm teaching you material or showing you insights, don't just watch the video once and forget about it. Make sure you watch the video, generate some output from the video, and then do that on repeat. And I'll be baking this into the activities that we'll be doing with each of our lectures. Now, the AI models, our base models, are similar, not exact, but similar in that if we have a prompt only interaction, right? Only prompting. This is essentially temporary context. Okay. It's temporary. Right? There is no permanent change. However, if I were to do some fine tuning, or either full fine tuning or parameter efficient fine tuning, PEFT, what we're going to have here is the ability to optimize my weights and also the biases, but in particular the weights. I'll be able to optimize those parameters of the model and eventually create a permanent behavioral change within that base model. This base model now becomes more focalized, more focused, and more specialized. Another way for you to think about it as a base model, this might be an undergrad student coming out of school, learning a few materials or a few disciplines, some general knowledge. Okay? But the fine tuning happens when they show up at work and they get their first assignment. And now they've got to get very good at a specific task or a specific set of tasks in a specific domain or industry. And now this is where we start to develop or build mastery. And that mastery is related to fine tuning in AI models. All right, so that does it for our 7 axioms. Now let's do a quick little activity here to tie all this together, just to make sure we're, again, using what we've learned. And we're not going to do any coding, but I do want to debug that IPM or information processing model. So let's take a minute just to think about a topic you tried to learn maybe sometime last year or maybe in years past. And not just any topic, but a topic you tried to learn and failed at. Maybe that was learning how to program, maybe how to dance salsa. Maybe you were trying to learn a foreign language. I want you to pick a failed attempt, and then I want you to think about or identify where that pipeline broke. Right? Was it the gateway or the gatekeeper? Was it the gatekeeper or the selective filter that filtered out some information? Was it the bottleneck? Was that the reason you failed at learning that? Was it just too much information and you were only able to get 4 chunks at a time? Was it your failure to use parallel processing? Okay. Did you not use your eyes and ears? Or did you not talk about what you learned with anyone? Was it the knowledge graph? Okay. Did you fail to hook that new information from that learning attempt to previous information that was already embedded and hardened in your natural schema? Was it that compression algorithm or the failure of using your compression engine that you had? Or was it the query function? Did you fail to retrieve the information after you ingested, after you consumed? Did you not try to recall that? Did you not use it? Did you not search your brain or use your brain to recall that information at a later time? Or was it from failure of the save protocol? Okay. Did you not use spaced repetition to consolidate the information you just consumed, whether it's a new language or a programming tutorial? Did you just take everything in, no spaced repetition, just watch a video once, put it away, feel good about yourself, check that box, and a few months later, you've forgotten it completely? So take a few minutes just to think about this. This is, again, just kind of our system autopsy activity for today's class. Again, no keys on keyboard just yet. All this is just essentially a thought experiment. But this should give you the opportunity to start retrieving and recalling some information and hardening some of the material that I've taught you today. Again, remember, we want to make sure we're processing actively the information that we're watching. We're not just passively consuming. What are today's takeaways? The key takeaways for today's lesson. The first one being the 20-watt bug. Now, remember, the brain runs on limited energy, about 20 watts of energy, and is designed to reject 99% of input just to conserve power. If you don't design the gatekeeper, which is our filtration system, then content gets filtered out. We also learned about the passive exposure fallacy. Input is not the same as storage. Merely consuming information without actively processing it results in volatile memory, and that is quickly deleted. Then we mapped our Magnificent Seven axioms. They're not random. They map directly to biological information processing model, that input, process, and storage diagram that you saw. Each of those 7 axioms help us prevent any data leakage or learning leakage as we are consuming information. And then finally, we did an activity, a system autopsy, and this will help us improve future learnings. But we first had to learn how to audit our own failures. Now, remember, failure is only failure when you quit and give up. Otherwise, it's just a lesson. Now, in the next class, we will go deeper on the gatekeeper, the first axiom that we previewed today. And once you know where your brain or your learning breaks down, you'll be able to patch it. And with the gatekeeper, we'll be able to engineer attention using prompt engineering logic, similar to what we do with an AI model. That's all I have for you today. Again, thank you so much for your time. Thank you for allowing me to serve you. Please do hit the subscribe button so that you're made aware of any new lectures that I post to the channel. And until next time, I'll see you guys in the next class. Have a great start to your week. Stay warm, stay safe, and keep learning.